In the previous lesson, we defined contours. In this lesson, we're going to talk about how to take integrals over a contour. We'll start with integrals over a smooth arc, and then we'll put the arcs together to do an example of where you have a contour consisting of several arcs. Recall from our earlier lesson on limits that the complex plane required a broader concept of limit and also of derivative, since the variable can approach its limit from an infinite number of directions. This two-dimensional characteristic also has an impact on integration of complex functions, and we saw that in the last lecture when we talked about taking the integral along a contour, which is basically a curve or a set of curves in the plane. So we'll start out with the Riemann integral from calculus, and then we'll generalize that to complex functions, and we'll see that in the next few slides. Okay, on this slide we're going to review the Riemann integral from calculus for real valued functions, and in a few slides forward we're going to generalize this for complex functions. So it's a good idea to kind of have a refresher here. Recall the idea is to find the area under a curve, a function f of x, between a point A and B, at least for real valued functions. And so the way we do this is we create little narrow rectangles below or above the curve. It dips below the axis, the x-axis, and then we take the limit as those narrow rectangles get smaller and smaller. So what I've written out here is sort of the math behind what I just said. You want to find the area under the curve f of x between the points A and B, and we break up A and B into a series of small intervals, and they're bounded by x1, x2, all the way up to xn, where xn equals b and x sub 0 equals a. And then the Riemann sum for this particular partition is defined as this sum here. So it's basically the width of the rectangle, this difference between any two of these x's here, and then f evaluated at some point in the interval. And the idea is that as you take the limit of these sums, as the delta gets smaller, if the integral does exist, then you'll approach a particular value. So I have a picture of this in the next slide, which may help a little bit to refresh your memory from calculus. So on this slide, which I've taken from the Wikipedia article entitled Riemann sum, we have this curve here, this black line, black curved line. It's the same curve, and what they're showing here is that you approximate the area between the curve and the x-axis. So if you go below, you take the area above. With more and more rectangles. See, here you start with fairly big rectangles, and the approximation isn't so good. Then you make the x's that we talked about in the previous slide a little bit closer together, and you get a better approximation. Then smaller yet and smaller yet. So if the limit of these various sums approaches a particular value, that gives you the area between the curve and the x-axis. So that's the idea. Now we're going to generalize that, but it's fairly similar to what we see here for the real valued functions. Okay, now we're ready to generalize Riemann sums over a smooth curve. And I've drawn this smooth curve down here on the bottom right, and we want to take an integral from alpha to beta, and just as we did with the Riemann sums over an interval, we're going to break up this smooth curve, and then we'll make these distances smaller and smaller. That'll be what we take the limit of. So you see here we've divided this smooth curve up into Z0 to Z1, Z1 to Z2, Z2 to Z3, all the way to the interval, just before the last interval here. So within each interval, we pick a point. It doesn't matter where it is. We just pick a point as long as it's in the interval. So this is the Z sub I stars. See, and you see there's one for each interval. The length of the intervals, 0 to Z sub 0 to Z sub 1, Z sub 1 to Z sub 2, they don't need to be the same. They can vary, but what we do is define mu of P sub n, where P sub n is the partition that we have here, and we define this mu of P sub n as being the maximum difference between these various intervals here. So, for example, maybe Z1 to Z2 is the biggest out of all the ones that we've defined here. So that's how we get started. Now it's gonna take a second slide to finish this off, but try to keep these definitions in mind as we proceed. So let's complete our definition of a Riemann sum for a complex function over a directed smooth curve. We have the definition here. It's Riemann sum over partition P sub n is the function f evaluated at Z sub I star, where Z sub I star, recall, was a point in a given interval, and then you just multiply by the length of the interval, and you add those together and you get the Riemann sum. So it looks very much like the real valued case, but we're not actually computing rectangles anymore. It's just a more general concept. What we want to do is force the partitions to have a maximum interval, this mu sub Pn to 0, and if we do that, then the limit of these partitions, the limit of these partial sums, should approach a particular value, which we call L, and that's the value of the integral. So let me say it again. F of Z is said to be integrable along gamma if there exists a complex number L, which is the limit of every sequence of Riemann sums corresponding to any sequence of partitions of our directed smooth arc gamma, such that the limit of the mu of Pn equals 0. And again, mu of Pn is the maximum interval length for a given partition. So we can write these words in this notation here. So whenever your sequence of partitions has mu sub P of n approaching 0, then the limit of the partial Riemann sums approaches L. Okay, and when that's the case, we say that f of z is integrable, and it's we write it here in terms of notation, the integral over directed smooth curve gamma of f of z with respect to z equals to L. We have some properties for complex integrals, which I'd like to go over here. The first one is that the integral over a directed smooth curve gamma of f of z plus or minus g of z is just the integral of each one of them separately. So very similar, actually exactly the same as what we have for real valued functions. Same thing for a constant. If you multiply by a constant, you can bring that outside of the integral. And then this one's kind of new. If you take the integral over minus gamma, which basically that means going in the opposite direction from what you've defined for gamma, then you just get negative the integral over gamma of f of z. Yeah, and I just wrote that out here, but so that's sometimes useful. If you want to change direction, you can just compute one or the other integral, and you'll get the other one automatically just by changing the sign. In the case where a function has a domain which is a smooth directed curve, we have a slightly modified definition of continuity. You see here in red is the difference. Let's just read it. A function f of z having a smooth curve gamma as its domain of definition is continuous on gamma if for any point z sub 0 on gamma and for every epsilon greater than 0 there exists a delta greater than 0 such that f of z minus f of z sub 0 is less than epsilon. Whenever z is an element of gamma, in other words, whenever z is on gamma, and z minus z sub 0 is less than delta. So the normal definition, or the typical definition, we just have this here, that whenever you have your z getting closer to z sub 0, then it forces f of z to be closer to f of z sub 0. Here we have an additional condition that z needs to be on a point on the gamma. So with that definition, we have this following sufficient but not necessary condition for a complex function to be integrable. It's if f is continuous on a directed smooth curve, then f is integrable along gamma. So there are less stringent conditions, but this one should be sufficient for our purposes. Okay, we have a theorem that's going to allow us to evaluate a complex function over a directed smooth curve without appealing to the definition of a limit. So it makes things a bit easier for us here. I'll read off the theorem. If f is a continuous function on a directed smooth curve gamma, and p of t is a parameterization of the gamma with t going between a and b, then the integral over gamma f of z is the integral from a to b of the composition of f with p of t times the derivative of p of t. So let's look at an example. Let's take the integral over gamma of the conjugate of z, where gamma is the left half of a circle of radius 2. And we'll have this parameterization of our circle, 2 for the radius, e to the I theta, and theta going between minus pi over 2 and pi over 2. So we use our formula here. We put in minus pi over 2 plus pi over 2. The conjugate of p of theta is 2 minus I theta. The derivative of 2I theta is 2, using the chain rule, is 2I e to the I theta. This term here, we can factor out a 2 times 2I, 4I, and then the e to the I theta times e to the minus I theta, these two here, gives you a 1, or e to the 0, which equals 1. And then the antiderivative of 1 is theta. And so when you evaluate the integral there, you get pi minus a minus pi over 2. And we end up with 4 pi I as our solution. We have a second example here. We're going to take the integral of f of z equals z minus z sub 0 to the n power over the smooth curve given by this parameterization here, p of theta equals z sub 0 plus r e to the I theta. This is basically a circle with center z sub 0, radius r. So we need to compute the two components of our formula from the previous theorem. F of p of theta, we plug in p of theta for z in here. We get this, and then the z sub 0 and the minus z sub 0 cancel. We get r to the n e to the I n theta. Then we take the derivative Z sub 0 is a constant, so its derivative is 0. Then we use the chain rule on e to the I theta and get I e to the I theta times R. So these are the two things we need for our formula. Plug this into here, this into here. We get this product. Then we can factor out an I R to the n plus 1, right? Because none of those involve the thing that we're integrating over, which is theta. And that leaves us with e to the I n plus 1 theta. There's two different cases when n is equal to minus 1 and when n is not equal to minus 1. And we'll evaluate those two cases on the next slide. Okay, let's complete our problem. When n does not equal minus 1, the antiderivative of this is e to the I n plus 1 theta divided by I times n plus 1. We evaluated 2 pi and 0. When you plug in 2 pi, you get e to the n plus 1 times 2 pi, which is 1, and divided by I times n plus 1. And then when you plug in 0, you get e to the 0, which again is 1. So these terms cancel and you just get 0. When n equals minus 1, you get r to the 0, so that's just the 1. And then within the integral, you get e to the 0, that's 1 again. So it reduces to this integral here. And the antiderivative of 1 is just theta. You take you evaluate theta at 2 pi and subtract it, evaluate it at 0, and you get 2 pi and times I, and that's our solution. We'll have occasion to use this result later on, and I'll refer back to example 2 from this lecture. In this example, we're going to have a function whose integral is independent of the given path. So we'll take the function f of z equals z over any directed smooth curve between any 2 points, z1 and z2, and we'll let p of t be a valid parameterization of our smooth curve gamma, such that p of a equals z1 and p of b equals z2. So we have our formula from the previous couple of slides where the integral of f of z over gamma equals the real integral from a to b of f of p of t times the derivative of p of t. And we know that since f of z is just z, f of p of t is just p of t. So we have this formula here. Now we need to find the antiderivative, but if we use the chain rule on this function here, p of t squared divided by 2, we get 2 times p of t divided by 2 times the derivative of p of t, and the 2 cancel. And so we get this, which is this here. So we know that p of t squared over 2 is the antiderivative. We put that in to our formula for that we've derived here, and we get that the value of the integral is p of b squared minus p of a squared over 2. And as we stipulated at the beginning, p of b is z sub 2, and p of a is z sub 1. So the final solution here is independent of the particular path gamma that we've taken. We'll see in the next lesson that there's other conditions where the value of the integral is independent of the path. So this is just an initial simple example of something that we'll see more of later. As we saw earlier, a contour is a concatenation of directed simple smooth curves such that the endpoint of the first curve is the initial point of the second curve, and the end or terminal point of the second one is the initial point of the third, and so on. So they basically all connect together. And in terms of integrals, the integral over the contour is just the sum of the integrals of the given function over each of the directed smooth curves that make up the contour. And in the case that the contour is a single point, which we allow for, then we define the integral to be 0. So in the following slides, we're going to do an example of a contour integral. The function is f of z equals the conjugate of z squared, and the contour is made up of 3 parts as we've shown in the figure here: gamma sub 1, gamma sub 2, and gamma sub 3. Basically 3 straight lines, which we've parameterized with these equations here. So just to let's take the middle one here as an example. So when you put in 0 for t, you get p of 0 is 0. When you put in, for example, 1/2, you get 1/2 plus 1i, which is 1/2, 1i, so it's right about there. When you put in 1, you get 1 plus 2i, that's here. So this function gives you this line from here to here. And the same for gamma 1 gives you the line from here to here, and gamma 3 gives you the vertical line going from 1 plus 2i down to 1. Okay, so we'll continue on the next slide with the evaluation of the integral. So we need to continue here to take the integral over each of the directed smooth curves that make up the contour. So over gamma 1, gamma sub 2, gamma sub 3. I just recopied this from the previous slide. Okay, so we'll first do it for gamma sub 1. We put in our function 1 minus t, excuse me. We take the conjugate of that, this is a real number, so it's just the same thing, 1 minus t, and then we square it. And then we have the derivative of this is minus 1. So our integral is from 0 to 1 of minus t squared plus 2t minus 1. We take the antiderivative and we get minus t cubed over 3 plus t squared minus t. Then we substitute 1 in. We get minus 1/3 plus 1 minus 1. And then we subtract 0 evaluated into here, but that's just 0. So we get minus 1/3, and the plus and minus 1 cancel, and we get minus 1/3. Okay, we need to evaluate the integral for the remaining 2 directed smooth curves. So next we'll do gamma sub 2. Now in this case, the parameterization is a complex number. So when you take the conjugate, you get t minus 2ti, and then we square that. So we get this here, and then the derivative is just 1 plus 2i. It's a constant which we can factor out. And we square this. Or actually what we can do first is take out a t. So we get t squared in here, but then what's left is 1 minus 2i squared, which we can factor out here. Then we take the antiderivative of t squared, t cubed over 3. When you multiply this out, you get 5 times 1 minus 2i. Then you evaluate it 1, which gives you 1/3. And then, of course, when you subtract, when this is evaluated at 0, you just get 0. So it's just 1/3 times this number. And we can write that out as 5/3 minus 10 over 3i. Okay, we're almost done. We do the last directed smooth curve. Again, we have a complex number here, so when we take the conjugate, we get 1 minus 2 minus ti, this thing here squared. The derivative is, derivative of 1 is 0, and then you get a minus 1 when you take the derivative of the minus I times t, minus I, I should say. So that goes here. I left out the details. I'll leave it to you to do the computation. It's a matter of squaring this, multiplying by minus I, and then just evaluating it 2 and subtracting the value at 0, and you get this here. And you can simplify that to 2/3 I plus, well, you have a minus times a minus, then the I times the I gives you a minus 4. All right, then you add all those together. From the previous slide, we had the integral over gamma sub 1 was minus 1/3. Then you have this term and the last term, and when you add all those together, you get minus 8/3, 1 plus I. So quite a bit of computation, even for a simple contour, but that's that's what it takes to get the value. So we'll have some more examples in the following lessons, but this is just the start.